Hello everyone and welcome. In this video lecture I will talk you through how to deal with free vibrations for vibrating beams. For that we are going to need the equation of motion again in its homogeneous form, so without the right hand side external force. We need the boundary conditions of a specific problem that we are looking at, as well as the initial conditions. So that means the initial shape of the beam as well as the initial velocity profile. So take note here that this problem has 4 boundary conditions because the spatial derivative is of the 4th order and we need 2 initial conditions since time derivative is of the 2nd order. So what we are going to do is we are going to make use of this powerful technique that we have seen before, and that is the modal analysis. And the cornerstone of modal analysis is the modal expansion, where we write the solution for the displacement field V as an infinite sum. Let me call it the sum of n is 1 to infinity of Vn times eta n, where, maybe I should emphasize that Vn is a function of x only and eta n is a function of time only. And this eta n is the modal coordinate of mode n. So this describes the behavior in time of the corresponding mode. So what we are going to do is we are going to rewrite this to the modal equations by substitution into the equation of motion. Let me at this stage use I as an index, so the sum of I of 1 to infinity of rho a times Vi times eta I double dot plus the infinite sum of EI times VI 1, 2, 3, 4th derivative, eta I itself, that is equal to 0. Let me now multiply by Vj and integrate such that we have this infinite sum of rho a times the integral of Vj times Vi dx. Eta I double dot can be taken outside of the integral plus the infinite sum of EI times Vj times Vi 4th derivative dx. Oh, this should be integrated, of course, sorry. Eta I equal to 0. So using the orthogonality conditions, we can show that these integrals are 0 for I not equal to j. For I equal to j, we have mass normalized them such that this first integral will be equal to 1, so it reduces to eta I double dot, and this second integral equals the natural frequency squared, so it's omega I squared eta I itself equal to 0, for I is 1, 2, and so on. These are the modal equations. Modal equations, and we have seen them many times before. They are of this simple form of an Esdorf equation, so we can immediately write down the solution that eta I as a function of time is eta I at 0 times the cosine of omega it plus eta I dot at 0 divided by omega I times the sine of omega it. And if you don't remember this solution by heart, just back substitute it into the differential equation and see that it works. So what are eta I at 0 and eta I dot at 0? For that we are going to apply the modal expansion on the initial conditions. So V at x, 0 can be written as the infinite sum, I is 1 to infinity, of Vi as a function of x times eta I at 0. and this must be equal to this prescribed initial shape. So let's multiply both sides of the equation by rho a Vj and integrate to obtain the infinite sum of rho a integral of Vj Vi dx times eta I at 0 equals rho a integral of Vj times V0 dx. So again, this integral only has a non-zero contribution for I is j. For that we have normalized it such that it is equal to 1. So eta I at 0 equals rho a times this integral of Vi, because I and j are the same, of V0 dx. So that means that if you know, as soon as you know what are the natural frequencies and modes, and you have mass normalized the modes, then Vi is known. Then as soon as the initial deflection is specified, V0 is known, and eta I at 0 can then be computed by doing this integral. In a very similar way, we can show that V dot at 0 is expressed as the infinite sum of Vi of x times eta I dot at 0, and this must be equal to V0 dot of x. Now, doing similar steps, we show that eta I dot at 0 equals rho a times the integral of Vi times V0 dot dx. So also the initial velocity of the modal coordinates can be computed quite straightforward. Then by back substitution in this expression, we obtain the solution for the modal coordinates as a function of time, and then by back substitution into the expansion, we obtain the solution for v as a function of time. So I would say relatively straightforward procedure. The most complicated part of it is probably in carrying out the integral to determine eta I at 0 and eta I dot at 0. But once you have obtained these, the solution of this problem is obtained relatively fast by back substitution. So that concludes the discussion on free vibrations. Thank you for watching. See you in the next lecture.